I knocked out last week when we were here. So yeah, we need to knock out this chapter on weather forecasting. I like it. And I think in all my classes, I'm going to have to kind of remind people about the electronic devices, so that I find it distracting. I can't say distracting. I find it distracting when folks are using electronic devices. Actually, I honestly, too, find it distracting when people are doing homework. Speaking of, you guys got homework? I got stuff to get back to you. So before we start here, I'm going to give you what I...
Can you answer this question?
No, that's going to be on your test.
Oh.
Yeah, for extra credit. Yeah. Okay, analyzing the weather. So this slide says, why would you care about the weather? Well, you know, one thing is if you're sending things into outer space, you care what the weather's going to be like. Okay, but everyday people care about the weather, obviously. Okay. I guess if you think about it, historically, a long time ago, you used to care about it more than you do now because we can protect ourselves from the weather, maybe more than we could before. So a couple of acronyms to kind of make sure we all know. The National Weather Service is generally local, not local, okay? So they're out of the Quad Cities or Peoria or Springfield, okay? And then actually you're going to want to know this acronym, I think, the National Oceanic Atmospheric Administration. Of course, you're familiar with NOAA, and that's the broader folks that keep track of the weather for here in North America. But honestly, it can't just be North America. We're going to see that NOAA actually coordinates with that World Meteorological Organization, the WMO, that we looked at a website the other day. Okay, so the National Center for Environmental Prediction, National Weather Service. Okay. So in general, it's at the local level that the forecasts are thought up. We're going to see actually usually it uses computers. So the National Weather Service folks come up with the forecast, and then they push them out there to the private sector for us. So a couple of branches, other important branches, the Storm Prediction Center in Norman, Oklahoma. Remember we talked about them when we talked about severe weather in the Midwest? Those actually give us our warnings, don't they? Nope, they give us our watches. Final answer. Okay, so Norman gives us our watches. Of course, we don't deal with hurricanes, but the National Hurricane Center we saw in the video today, that's out of Miami. Okay. So yeah, looking more broadly, we have the World Meteorological Organization, or WMO. Last year when I was getting ready to do this topic, I looked for some flowchart that had this kind of concisely on it, and I couldn't find one. But just think of WMO as being worldwide. And so they actually have centers in D.C., Washington, D.C., Russia, and Australia. So there you go. So the WMO, the World Meteorological Organization, coordinates efforts of weather forecasting and current conditions through their centers. So one of the things that's important to those computers giving us a forecast is what we call initial conditions. So at the top of the slide, if you want to write initial conditions, that's kind of what we're talking about here. Current atmospheric initial conditions. Makes sense. Your computer doesn't know what the barometric pressure is. Your computer doesn't know what the moisture content is. Computer doesn't know wind speed. It doesn't know cloud cover. Okay, so we need initial conditions to give our computer. So actually, there's an assortment of ways to get those initial conditions. We can get them through land sources, and a major land source are going to be those ASOSs. The ships out there can send us back initial conditions. We can get them remotely from those little water buoys that are in the oceans. We can get them from planes. One of the problems we have in forecasting the weather here is it's such a global sort of thing that we have these dead spots here and here, you know, over large bodies of water. Heck, we even have dead spots, as you might imagine, in unpopulated regions of the world, okay? But initial conditions are what we need to feed our computers in order for them to spit back out a forecast. Weather balloons sent up twice a day, okay? We talked about weather balloons in the previous life. No, in the first unit, actually. So of those 10,000 land sites, 1,000 of them are operated by the United States. And many of those fall into the category of ASOSs. So ASOS. And actually, I think I have a slide coming up to remind you what that stands for. So those land sources, what do our computers need to spit us out a forecast? They need to know current conditions, initial conditions, temperature, humidity, pressure, cloud cover, wind speed and direction, visibility, fog, and precipitation. Does that ring a bell for what those little cute little ASOSs can spit back? Okay. So here are those ASOSs, which again, those are maybe 1,000 or so associated with the United States, spread out. A lot of times these ASOSs are actually run by the FAA because their pilots need to know the same things that the weather folks need to know. So they're pretty cool. Automated surface observing systems. So when we talk about weather balloons as giving us information, the previous slide says they're sent up twice a day, and they are sent up twice a day. And remember that as they go up, they can measure things like the current temperature, the current pressure. If they are the next thing I have, if they are not a radio sound on the weather balloon, but the little box is instead called a RON sound, they're very similar, but what the RON sound does is tell us wind speed and wind direction. Okay? And remember that the weather balloon actually gets larger and larger and larger because of the less pressure. It gets the size of a house. The latex can't support it being extended like that. It breaks, and the thing floats down. Okay. So weather satellites fall into two categories, two types of weather satellites, and they differ by how far above the Earth they orbit. So the things, of course, you guys know satellites. There's communication satellites and there's weather satellites. What they have in common is they orbit the Earth, right? They're gravitationally bound to the Earth, and they orbit the Earth. Okay? So the two types, this is the first of the two types. It's called polar orbit satellites. And actually, the Hubble Space Telescope is like this. And actually, the International Space Station is also like this. They orbit from pole to pole, and it takes about 90 minutes, an hour and a half, to go to do this once. I think regardless of if it's one of these weather satellites, whether it's the Hubble Space Telescope, the International Space Station, an hour and a half. That's why if you're looking for them to pass, look for 90 minutes later and they should pass again. But the thing about these polar orbits is that they are kind of higher than the other orbit I'm going to talk about. They're really good if you want to see the poles, take images of the poles, but actually, as you might imagine, it's kind of hit and miss because the Earth is spinning, okay, as this is orbiting, so it's kind of hit and miss over the middle latitudes. So those are called polar orbit satellites. The other type of satellite is called a geostationary satellite. Okay, let's see, 36,000 kilometers. Make sure I got this right. Oh, I was wrong. These are lower. Okay, so these are lower. I told you higher. These are lower. So compare 850 kilometers to 36,000 kilometers. Okay. So the other ones actually orbit near the equator, okay, but they're called geostationary satellites because as the Earth rotates, let's find North America because that's who we care about. As the Earth rotates, okay, so also the satellite is orbiting the Earth. So it basically hovers over one region. Okay? We actually have a pair, at least, of these sort of geostationary satellites. We call them goes east and goes west. So they hover here, and they actually are between goes west and goes east, getting a full coverage of what's going on in the United States. But these, like I said, these are up at upper elevations versus the ones that orbit the poles. So as far as what sort of images these satellites can get, first off, the way they work is basically they take a scan for, I think it says it takes 30 minutes to get a complete composite image. And they can actually scan at different wavelengths, and that gives us different images. So the different wavelengths we can focus, or they can focus on different aspects of weather. Go figure. So the visible ones can kind of show you cloud cover. But one of the things, and maybe this makes sense, but if the sun's over there, okay, let's make the sun kind of where the clock is right now. This would be daytime, and this would be nighttime. Okay, and do you see where if we have a geostationary orbit or GOES satellite here, that actually it can't see any, there's no visible light coming from North America because the sun's over there and it's nighttime. So your visible images from your satellites, they're screwed. But actually you can get images from, if you change the wavelength. Instead of looking for visible light, if instead you look for a heat signature, infrared, that works. So we can get infrared images at nighttime, and we can also change the wavelength and be selective for water vapor. And so maybe the obvious is if you see a patch of lots of water vapor, that's the potential for precipitation, or fog or something like that. So here are some images, visible, and that's the GOES. Let's see, probably looks like the GOES East, GOES 8. Okay, and I think these are all taken the same day, September 12th, 08. So the first one was visible. This one's infrared. It's kind of like, what was that movie with the dude had the infrared? A lot of movies, the dude had the infrared. But this is looking for a heat signature. And remember, we talked about if you have high clouds, those clouds are going to be very cold because basically they're rising and cooling, and so you're looking at cold cloud tops right there as an indication of instability. And this one's water vapor. Those two really go together, don't they? This is GOES 8, that's GOES 12. But anyway, you can actually kind of see this is not radar, okay? It looks like it should be radar, but it's not. It's from a satellite. It's basically a thermal signature looking for those cold spots in those clouds. And you can see the instability right there in the cloud in the moisture. So we talked about 3 scales of motion way back when. I think it was the Unit 2. We talked about the small scale, micro scale, the mesoscale, and the large scale was actually the planetary or synoptic scale. So these synoptic weather maps are large, okay? And so when we look at I was trying to show you something interesting, like a surface map, but when you look at a total map of the United States, that would be like a synoptic weather map. I couldn't find anything that was classic. So these are examples of synoptic weather maps. So you're probably used to seeing these on the internet. So if I was to ask you, related to what we talked about before, does that look like a mid-latitude cyclone in its mature stage? I think so. You can kind of see the characteristic 3 weather fronts, the occluded, the cold, and the warm. Okay, so this is a synoptic weather map. And so like the previous slide said, these used to be drawn by hand. And remember, the way this works is each one of these is called a little station model. So as I'm circling there, remember, if you have a key, you can actually understand cloud cover. The 2 temperatures are current temperature and dew point temperature. Okay. So I mentioned the whole thing with computers. I kept saying computers need initial conditions. So when you think of numerical weather prediction, numerical weather forecasting, think of computers. So basically, this thing with the model, this word model right here, numerical forecast models, those are like little programs, okay? Those are like little programs. And I've heard it described like this, that meteorologists will, you know, get used to what programs work, what models or programs work, and what models or programs don't work. Maybe it's even selected for a certain time of year, but they kind of go to their closet and pull out a model. There are certain internet websites, and I think the Weather Underground does this, where you can actually pick on which model you want to use, and they will tell you what the forecast is according to that model. Okay, so those models come from knowing how the atmosphere should behave based upon initial conditions, which may or may not be the case. As you know, forecasts go wrong. Okay, so think of that when you think of models. So these different models have strengths or weaknesses. Like I said, I think when if you're in the biz, you know which model to use. I might have mentioned before, but I took a group and we toured in Chicago, one of their news stations downtown, and we actually met with a meteorologist who showed us his back room with all the computers and stuff. And it is where he would kind of go and say, you know, what makes sense to him. He had the final say in basically what was disseminated to the public. So initial conditions, and remember a few slides ago I had you put the word initial conditions, where it had the whole thing about the weather balloons and the water buoys and the ASOSs. Those give the initial conditions that are plugged into the computers. Okay. So what do the computers do? Well, the computers go something like this, and they do it very quickly. Okay. First off, and I'm not going to emphasize it much, but sometimes there's a smoothing process that needs to go on the front end before you feed your computer a bunch of stuff. Thou shalt make sure it makes sense. And, you know, you throw out outliers and that sort of thing. But once the computer gets it, what the computer does is basically say, all right, based upon this model you want me to use, I am going to tell you what the forecast is 2 minutes from now. You're like, dude, I don't want it 2 minutes from now. That's not going to help me. I actually want it like 2 hours or, 8 hours from now. But what it does is it's kind of a piggyback sort of thing. So if down here on the bottom, if this is time, okay, what it does is basically it goes forward 2 minutes and it comes up with a forecast. Forecast. And then it takes that forecast as if it were new initial conditions and it plugs it into the same model and it comes up with 4 minutes in advance. Okay, so it plugged this forecast in as initial conditions. Whatever the forecast is at 4 minutes, it plugs it back in as initial conditions and it comes up with 6 minutes. Okay, and it does this very quickly. It comes up with 8 minutes. Okay, so it's just kind of eking on into the future. One of the things you guys already know is that if you go, if this is time out here, out here, the farther out in time you go, the more uncertain the, usually, yeah. Yes, exactly. The more uncertain the forecast is. So that's kind of how that goes. So it kind of piggybacks. So those are a lot of calculations. Now, these models, these programs in the background that are running, they're very complicated. And if you've ever heard that Benjamin Franklin actually was kind of the father of predicting the weather, it's true. The thing about Ben Franklin, on the crudest scale, I guess, what he did was basically over here. I don't know how far west because it's pretty early. He had kin here and he was here. So basically what Ben Franklin could do is basically see, one of the things we know is that weather tracks for us, usually because it follows the mid-latitude westerlies. So he's like, hey, I can predict the weather via horse. But this idea of having a program, a set of mathematical stuff in the background to plug in initial conditions. A dude back in 1700s came up with the idea, but that was way before computers. So here he is, he's like, I can understand the atmosphere, and I can understand plugging in these initial conditions, and I can understand forecasting, giving a forecast. But by the time he crunched all the numbers, okay, for the forecast for tomorrow, it was like a week later. So that was problematic. So computers were really needed to come in to play before we could really get our numerical weather forecasting under control. So progs, or prognostic charts, are basically what the computer spits out. So it can be tweaked by these statistics, kind of what you know about your program. So I hope you get kind of a sense for there's different programs, you know. So it's like, which program do you pick on? Which program do you choose for a certain time of year for a certain location? So actually here when we talk about accuracy in weather forecasting, I'm going to take us to a website where they actually compare how correct are these different websites for being accurate or not. So the atmosphere is very complicated, and one of the pitfalls is, remember those initial conditions that come from weather balloons, that come from blah, 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 ASOSs. That mass of data, actually, any data has uncertainty associated with it. And actually, that can give you problems, too. So speaking of, related to the movie, the butterfly effect, there is this butterfly effect in meteorology. As I understand it, the term butterfly effect actually came from, if we pick on South America here, came from the fact that supposedly a butterfly can disturb the atmosphere with its wings, and that disturbance propagates through worldwide, and it has effects everywhere, including here. Okay. So the butterfly effect, though, here is, and so that's with the butterfly, you get one set of outcome, and without the butterfly, you get a different outcome. Okay, so two very similar sets of initial conditions, one with or without the butterfly, can develop into something totally different. So kind of related to that is this concept of chaos. I should stick my pinky in my mouth and go, So chaos is a lovely thing in physical science. Chaos is a lovely thing in life. Chaos hits my house quite often. Chaos just means kind of disorganized. So in this sense, chaos means actually those initial conditions you think that you're plugging in, there could be some wiggle room in all of those initial conditions, which would have a totally different outcome, kind of like the butterfly effect. So they're definitely related. So as we're talking about initial conditions, if we just pick on a single temperature from a single location, right at the freezing point temperature, 32 degrees Fahrenheit. So some of you guys are familiar in the term tolerance. So all measuring devices have a certain amount of tolerance. So let's just say that thermometer is plus or minus 2 degrees. That's pretty good. So what that means is, in effect, it would be within tolerance, and they would be correct values displayed by that thermometer if it was any of these. Okay, even though it displays 32, since it's plus or minus 2 degrees, it could really be 30, 31, 32, 33, 34. And actually that right there is your set of possible real temperatures. Okay, real temperatures. That you're like, which one do we run with? Well, you run with the 32, but you know that there's that play in that temperature. That's only one temperature, okay, amidst a sea of data. Okay, so that's kind of what they're up against. So one way to combat the butterfly effect or the chaos effect is this idea of ensemble forecasting. So if you've ever played in a musical ensemble or sung in a musical ensemble, that's the way I think of it. Basically, you are a set of people trying to put forth beautiful music. So in ensemble forecasting, basically you get a set of weather forecasts, okay, trying to forecast what tomorrow's going to be. But for that set, I'm going to show you like a set of 50. For that set, basically you have only changed the initial conditions slightly. Kind of like the whole 30 to 34 Fahrenheit sort of thing. Okay, so you come up with a set. And then what you do after you have a set is that you look for a pattern. Okay, so in the example I'm going to show you actually of the 50 forecasts, it was an important day in Europe, okay? And on that important day, if they had done this ensemble forecasting, they would have perhaps forecasted for the nasty weather that they got, okay? So you look for a pattern, and if you look for the pattern, and that will give you confidence in what you disseminate to the public. I don't know, you guys probably buy this, forecasts can save lives, okay, done correctly. And that's kind of what they came up with. So the other thing with ensemble forecasting is it can actually, because you're using the same model, you're using the same program, you can see if there is an issue with your program or model that you're using. So here we go. Here's the example of ensemble forecasting. Well, I guess it's on the next slide. So what I'm going to show you here in a minute is a bunch of little boxes. Those boxes are an assortment of 50 different forecasts, okay, done with the same program, or not changing models, but done with just slightly differing initial conditions. So at the top, you're going to see 3 frames. The first 2 are what they broadcast. The third one is actually what happened. So like I said, if they had gone with this ensemble forecasting approach, which seems like a pain in the butt, they would have seen a pattern for the severe weather that they actually got. Okay, so there's what they forecasted. And you can kind of see the low pressure. The colors up there are the precipitation, right? And here's what they actually got. So definitely tighter isobars than they thought was going to be, and significant precipitation. And I think this was, didn't it say the date was Christmas Eve, 99, yeah. Not a good day to get the forecast wrong. They got a white Christmas, but they didn't forecast it. So here's the set of 50, okay? So if I'm just eyeballing it, kind of looking for that nasty weather, you know, I might would circle this one, this one, this one, this one, okay? Instead of going with the hardcore, middle-of-the-road initial conditions that they went with, okay, if you were to change up those initial conditions slightly, okay, you see definitely a pattern for this. So it's a possibility, and it can actually help combat the butterfly effect or chaos effect. Okay, so the National Center for Environmental what?
Protection?
No, I can't remember what NCEP stands for environmental prediction. Okay, forecasting prediction. Thank you, though. So the National Weather Service issues our forecasts in general, but in order for those forecasts to be issued, before they're issued, they wade through the data that's coming in, basically. And they get veto, like when I went to that tour to the forecasting there in Chicago, he gets to veto what the forecast model says. And then they eventually disseminate it to the public. So if you're like me, I just don't quite understand the intersection between the National Weather Service and like Weather Underground. I don't get it. So I'm just talking as if National or the Weather Underground isn't a player, but it is definitely a player. Oh, here's my bloopers. So I went out and found some bloopers. So this is a good, we'll watch some bloopers and then we'll take a break.
Are there bloopers?
What's that?
Weather bloopers?
Weather bloopers.